Let us start lecture 10 and we will look into the concept of equilibrium in the on the basis of internal energy and entropy. Now, we have understood how entropy is created during irreversible process, and that entropy creation is always positive. So, that means in case of irreversible process there will always be some loss of work, and that loss of work is actually converting into heat into the system. Okay. So, that is what we have to look into how into the situation how we can actually relate our equilibrium on the basis of entropy. And when we talk about entropy, we would also look into how it actually considers internal energy concept to explain equilibrium. Okay. Now, as we see that the concept of equilibrium on the basis of entropy and internal energy, that will be the topic today. So, we have what we have considered? We have considered that if it is expansion or contraction on the basis of evaporation as well as condensation of vapor from liquid to vapor or vapor to liquid, we checked that the generic equation becomes del S system equal to Q by T plus del S irreversible. So, this is for let us say expansion or evaporation. Please refer to lecture 8 and 9. This is let us consider evaporation. So, this is the generic form, and also del S total equal to del S irreversible. So, this del S irreversible is greater than 0. It actually indicates loss of work which converts to heat in the system. Fine. Now, let us check a situation of adiabatic irreversible process. Adiabatic irreversible process. When we take adiabatic irreversible process, so that time let us say P A, the pressure of an ideal gas goes from P A to P B, and since it is adiabatic system, so it is isolated. Let us consider that if it is isolated. So, then this process would have some work loss. So, that work loss converts to some amount of heat within the system. Now, had it been reversible, then I could have said that del U equal to minus W, okay, delta U equal to minus W, and this is reversible had it been a reversible process, because Q equal to 0, Q reversible is 0. So, this is isolated, that is what Q is 0. So, this is reversible adiabatic expansion, and it would maintain, I mean it is an ideal gas, it will maintain this P V equal to constant, that surface it would have maintained. But once we have irreversible process, this is irreversible process, the system would come out from that equilibrium plane. Okay. And when it comes out, there is some amount work is lost and some heat is generated. In this process also, we would finally see that del U prime equal to W minus W, because it is an expansion, the system is doing work. So, that case also it will maintain like this, but since there is some heat generation, that heat would be incorporated into internal energy. So, the internal energy change, and or I can say the other way around, it could be, so this is, let us not take that internal energy term, or we can say that it would, the final temperature irreversible would be little greater than final temperature reversible. So, that means the internal energy would be little higher of the system after adiabatic irreversible change in comparison to the system where adiabatic reversible expansion change is taking place. Finally, it would be again the change in internal energy would be equal to the work done, but we are not getting the expected internal energy change in order to get more work in comparison to irreversible when it is irreversible process. So, I can see that W reversible is greater than W, which is irreversible. So, this is irreversible, I can put irreversible, and that time my del U would be, if we see magnitude, would be little less than, this is del U, let us say del U irreversible, the magnitude would be little less than del U reversible, if I take magnitude only. So, had it been reversible, the internal energy change would have been, it should go negative side, because this work component is positive. I can write this equation as W reversible equal to minus del U, or W irreversible equal to minus del U prime. Okay. So, this del U prime is nothing but this part. Okay. So, internal energy has to reduce in case of adiabatic change irrespective of reversible or irreversible in order to get some work, but if it is reversible, I would have gotten a much more reduction in internal energy to get the work maximization. But in case of irreversible process, I will not get the that much amount of internal energy decrease, because some amount of work is lost, and that some amount of work is actually manifesting into entropy change in the system, which has to be positive. Okay. So, now at least from this discussion we can sense that in case of reversible case, since I am getting the maximum work, reversible expansion case for adiabatic system, I get the maximum work provided the internal energy goes minimum. So, reversible adiabatic expansion internal energy minimization should get me work maximization. And in case of irreversible process, internal energy still would reduce, but it should be the magnitude of that reduction delta U would be less than the magnitude of reversible delta U. That is what we are getting less work, but remember there will be entropy change in the system, and that entropy would be irreversible entropy, because some amount of work is lost. Now, at least I could sense, another thing I could sense is basically when there is an irreversible process, entropy tends to increase and internal energy tends to decrease. And at some point of situation that had it been irreversible, had it been reversible, then entropy should have been maximum and internal energy should have been minimum. Okay. That sense, that gives the sense from this particular discussion, because getting work from adiabatic expansion, there should be reduction in internal energy. Okay. And when it happens, if it is irreversible process, there would be entropy creation, and as it goes towards the reversible mode, internal energy change should have been maximum and internal energy should have been minimum. The internal energy should have been minimum, the change of internal energy should have been maximum. Okay. So, that is the condition we are sensing. Now, let us look at this equation. Del u, we have seen q minus w. In fact, if I consider only mechanical work, so then, and if we consider reversible process, so reversible process is nothing but it is the system is going through a subsequent infinitesimal stages. So, every time the system undergoes through a kind of equilibrium considerations. So, I can write del u equal to T del S minus P dV. I can write this considering only mechanical work and reversible process, and this is nothing but reversible. Okay. Now, when we write this, let us, when we see this, in order to understand the change in U, I can take entropy and volume to be my independent variables. And let us say this is also a closed system, and we are taking it as fixed composition. Okay. So, I will actually come to this fixed composition when we take chemical potential into our picture. So, when we have this, so that means I can write U equal to function of S and V. So, I can write del U equal to I can write this. So, if I compare this and this, these two equations, I can get like this. Now, if we say del U S and V both are constant, so it goes to 0. Okay. So, that means that suggests that the change in internal energy under constant entropy and constant volume is 0, and that time it reaches equilibrium. And what happens to U? We have understood from adiabatic expansion, if it is, then the internal energy has to reduce to get some work. So, that means in order to reach, and when it is reversible, which is equilibrium consideration, the internal energy should go to minimum, and when it is minimum, that means it has to be del U has to be 0. Okay. So, and here I am seeing that constant entropy and constant volume process where the system is closed. So, that time this is going to 0 and U goes to minimum. Okay. This is one equilibrium consideration. Okay. Now, let us take other way around. If I take S is a function of u and v, then I can write ds equal to, so let me write it, okay. So, that case I can say that ds u v equal to 0 when internal energy and volume are constant. So, this is also concept of equilibrium or condition of equilibrium. Now, check the adiabatic expansion process. So, there we saw that when we talk about some work coming out from the system, we see that some amount of work is lost during irreversible process. Now, as we go on to have that process at a much lesser degree of irreversible process, the work, loss of work would be less. But if we go on to have a greater degree of irreversible process, the loss of work would be very high. So, the entropy generation would be very high. Okay. So, now if I see the internal energy change, as we see that internal energy goes to minimum in case of reversible process. So, that means in case of irreversible process, we saw that entropy has to increase in the system. Is that correct? Because, so, that means there will be a situation when entropy would reach maximum, and that situation we can have this. So, we can say that entropy goes maximum under constant internal energy and constant volume. Constant volume. So, this is nothing but, I can take it as an isolated system. Okay. So, that means I could see that isolated system, the entropy goes to maximum when the system reaches equilibrium. So, I can say that this is another condition of equilibrium. Okay. So, I could see that there are two conditions: closed system, fixed composition, u goes to minimum when the system is taking place under constant entropy and constant volume, and there is another situation where entropy goes to maximum under constant u and constant volume, and this is also a concept of equilibrium. Okay. So, now we could see that del S, let us go back to this equation, du equal to T del S minus P dV. In fact, this is the combination of first and second law, this equation. So, if I carefully see this equation, in order to define a system, that means definition is possible when the system reaches equilibrium or a macro state is achieved. So, that time I need to see how that particular macro state is achieved. I need to control or measure some of the independent variables. And what are the independent variables here? Independent variables are S and V. These are basically two independent variables. Okay. These are the two independent variables. Now, we always try to look at the system definition using some parameters which are easily measurable or easily controlled. Okay. Now, we have to check whether the volume and entropy both are easily measurable or easily controlled. Now, if I try to look at volume, it is still relatively easy, but entropy cannot be easy. This is very difficult parameter to deal with. So, then we have to look into some other factor or other variable in order to define the system, and due to this particular difficulty of defining the system with the help of independent variables of S and U, even if I try to check this del u by t plus p by t dv. So, here I see independent variables become u and v, these are independent variables. So, I can actually define the system with the help of entropy while taking u and v to be my independent variables. So, u is not a kind of easy parameter which can be controlled easily. So, then we go to define some, these allows to think a bit, and we bring in auxiliary function. And what are the auxiliary function we will bring in? Helmholtz free energy, another one is Gibbs free energy. And interestingly, this is termed as A, this is termed as G. And what are the other variables which are possible? The other variables which are possible are other variables. If I try to look at, one is pressure, temperature. Okay. So, if I look at this pressure and temperature, it is very easy to determine the pressure and temperature of any system. And once we take the definition of a system on the basis of pressure and temperature, I can easily measure those two parameters, as well as I can easily control those two parameters to decide how the state changes or the system changes from one state to another, okay, one macro state to another macro state. So, we finally come to a situation that for easy definition of system or the system equilibrium, we take up three parameters to be independently varying. One is P, T or V, because P and T both are easily measurable and controlled, but V is still little difficult, but it is still very relatively convenient to measure or control. Okay. And interestingly, these two variables are actually, these two free energies or the auxiliary functions, they can also define the system, and this is defined as this. Okay. And finally, it leads to a situation of minus T minus S dt and minus P dV equal to du, sorry, this is equal to dA, and here it comes V dP minus S dt equal to dG. We will see these two forms later. Okay. Now, here you see that the first one, that free energy, Helmholtz free energy, the two independent variables are temperature and volume, and the second one Gibbs free energy, the independent variables are pressure and temperature. So, I can easily control those two variables, and I can decide the situation of the state of the system or equilibrium state of the system. Even we can also take see how this one particular state to another state, when it goes, what happens to those parameters. Okay. So, that will be the very convenient way of defining the system. So, that is what the auxiliary functions are brought in. Since some of the independent variables like internal energy, entropy, those are very difficult variables and inconvenient variables. Okay. So, now we could see that the auxiliary functions are important. Now, most of our metallurgical processes or materials engineering processes, we consider pressure and temperature to be our independent variables. Okay. So, metallurgical or materials engineering we consider pressure and temperature to be independent variables, and that is what we try to define those processes with the help of, or those system situation or equilibrium condition with the help of G. Now, V and T are also taken up. So, this is considered when, so that means a system of constant volume and temperature. So, that means I have a so that case we take A as the free energy to define the system. Now, this is useful for explaining defining equilibrium on the basis of statistical mechanics. Mechanics considerations, because once we have a control volume, or the we can say that constant volume, I can take quantization of energy easily. Okay. So, this is related to this. So, there we consider constant volume and temperature, constant temperature situation. Okay. But otherwise, for our phase diagram calculations, in case of mostly we will deal with condensed systems, and single component we consider one vapor phase, whereas in case of binary systems we will consider only the condensed systems like liquid and solid. So, there we will be absolutely fine considering G as our defining parameter, and the variables would be pressure and temperature. So, let me stop here. We will continue our discussion on these auxiliary functions. So, at least you could sense that auxiliary functions are brought in order to make things easy to understand systems condition or systems equilibrium. Thank you very much.